All right, thanks everybody for coming. I know it's a really busy time. There's midterms, all kinds of other things going on, but we really appreciate you taking the hour out of your day to be here. There's a lot to learn today. So I'd like to welcome our SVLS speaker, MJ Lee, who is currently a Senior Principal Hardware Development Engineer at Oracle. So a little bit about Mr. Lee's background. He holds a Bachelor of Science degree in chemistry, which is near and dear to my heart because I'm a chemical engineer by training. And he has more than 30 years of experience in the packaging and assembly industry, chiefly in advanced package and material development and deployment. Prior to joining Oracle, MJ worked at Xilinx and Altera for 15 years as a principal engineer and senior manager of package development. He's also worked at National Semiconductor and Amkor Technology Korea. At Oracle, Mr. Lee's responsibilities include developing advanced IC semiconductor packaging technology and productization. So please help me in welcoming MJ Lee.
Thank you. Thanks for the kind introduction, Cheryl. It's good afternoon. So I also thank for giving me this kind of a great opportunity to giving my talk about this IC packaging technologies. So I'm not sure whether you are familiar with this, the packaging technologies in IC semiconductor field. But this is a very specific area in very broad the semiconductor the field. So again, my name is MJ Lee. I'm Korean. Moved to US about 20 years ago. I used my name as MJ. I remember it was about 1986, 1987. At that time, it was in Korea. The company just introduced email system. So every engineer has to come up with their own email address. So what is the best one is instead of using a long kind of Myung-June, then some Americans, the pronounce it Myung or Myung. So okay, MJ is better. So I used MJ Lee, and then from that time, I was called by MJ. It's not Michael Jordan, or Michael Jordan, Michael Jackson. But my friend called me a Michael Jordan when I play basketball. I'm very athletic. I do swimming for about more than 30 years, and I practice kendo, one of a Japanese martial art. So I'm good in athletic. When I sing a song, they call me Michael Jackson. But they never call me Mary Jane. So today, this is a CPI. So CPI is a chip-to-package interaction in IC semiconductor packagings. I will be after. And then there is a lot of technologies got involved on this area. So today's content, I like to address what is going on in the world in this technologies area. And then we'll go very general definition of chip package interaction, so-called CPI, and how this IC packaging has been developed, and what is the journey of IC packaging, and go a little bit deeper. So what is the packaging technologies that has some drivers and the future roadmap. And eventually go to real elements and realities of CPI. And then we can briefly discuss about the roles in these packaging technologies. So before go to the talk, I shared this article with the seller about a month ago. One day I happened to read one of the article from IEEE, was by Robert Locke. I don't know him in person. But it was very kind of interesting and funny, the 70% rule. When imperfect understanding is best. So to make it short, he attended one of the conference, and after 2 days and 3 days, the conference, he realized, okay, I have two distinct the categories. One is I understand the things almost entirely, and the other category is I hardly understand at all. So what is the ratio? But end of the talk or end of the presentation, his question was, okay, how many percent of audience will understand what I've been talking about? How many are not? And then he put 70%. There is no clear rule whether 70% is absolutely good or making sense, but he just put 70%. So after reading that, I asked two of my friends. They are teaching in the university, in different university in East Coast. So what do you think? And the one guy responded, maybe mine is fall into 30%. Wow, then the teaching might be very challenging. And the other guys told me 60% he generally talk to his student. So when student present something, his study or theories, if you are not sure the audience will understand about 60%, don't go and present. So what is mine? I have no idea. So I just take average of 70, 60, and 30%. It comes 53%. So hopefully end of this presentation, I could have about 50% of students understand what I've been talking. So first one is force driving technologies. What's going on around the world? So there might be a lot of the factors driving technologies in the world, but in semiconductor, I personally put these three factors. One is the performance. So a lot of data demand from cloud, internet, and the cell phone, everything. And the system compute also require very high level of performance, speed, and bandwidth, also speed here. Form factor, like the old IBM supercomputer is big. It takes a big room, big facilities. But this day, the form factor is another important factor. Like Internet of Things, everything is gonna be very small, tiny, but perform very well. What the consumer asks for. It should be faster and smarter and smaller and thinner, which can we attach on the suit or on body. And the flexible. Cost is important factors. So it's consumer product, everything, automotive, the cost. Very cost effective. So from design stage, it has to be designed for cost, the consideration. And that should be high volume manufacturable the product. So HVM, designed for manufacturing, and then time to market. Someone changed it to time to money. So eventually, yes. So in our performance side, we have a lot of high performance computer, network, and the big data, and then AI. AI is becoming very hot these days. And in order to support, the packaging has a lot of innovative technology, 2.5D. So the 2D is two-dimensional, so one silicon chip and the one package. And then 2.5D is in between 3D stacking. We put the passive interposer, which can support more higher density interconnection with a very fine line space design rule. And moving forward, 3D as kind of homogeneous dies stacking, 2-stack, 3-stack, 4-stack, like the Micron or the Samsung Hynix memory cube. Those are all connected by some bumping or wire bond interconnection technologies. And eventually, we're moving to direct wafer-to-wafer or chip-to-chip connection without using any bump or any interconnection wire bond type of technology. So they call it a wafer-on-wafer or chip-on-wafer. So finally, it has a stack die and stacked package, POP, package on package, silicon in package. Those things are supporting this very high-end performance area. And the form factor is mainly for this market, like mobile electronics. So we have wearable things in here and some smartphone connected to car and the home and everywhere. So those should be very small, very tiny. So small form factor, thin and coiless and flexible and wearable. In that area is a wafer level chip scale package, the fan out wafer level, the fan out panel level packaging. Maybe you don't understand what I'm talking about, but maybe a couple slides later, we could show, I will show some the visual aid. In the cost side, this one is a very good idea, innovative idea, but still we need squeeze more cost. So 2.5D, what are the more cost-effective technology which can bridge the interconnect chip to package effectively? So that is the embedded multi-die bridge invented by Intel. So why we need passive silicon interposer? Just put the bridge, embed the bridge inside the substrate. That is EMIB. And Amkor, one of the assembly technology company, they came up with some different idea. So for the large body size, shift, and it's a small area, it's a slim, okay? And then ASE in Taiwan also have similar kind of alternatives. Fan out chip on substrate. There are so many other kind of innovative, cost-effective alternatives there. And moving forward, we don't need a bump. We just go to copper in wafer side or triple wafer side, direct bonding. So those are one of some kind of example of what they have now. And this is just copper on the top die and the bottom die connected together. Eventually, all these technologies will enable the entire world, everything get connected together. So smart home, smart city, and smart factory, even smart farm. So people can stay at home in Ohio and then a manufacturer running his farm in Alaska. And autonomous car is becoming very popular. In 2030s, Germany is not going to allow any gas car. That is what I read some newspaper several weeks ago. And even medical, artificial intelligence are going to connect everything together. So from that drivers, we go down to what is the CPI. So definition of CPI is pretty wide and detailed, but I would like to take very general definition. So it is interaction between IC package and IC chip device. So IC package is mostly organic, and the silicon IC chip is the silicon. So there is the two material is really different hardness, different material property, big CTE mismatch in between two. And also, within that chip package, other interaction of stress between each different heterogeneous layer. Like within silicon chip, there's a silicon and the dielectric film and the copper, so different layers. Even package has some encapsulant between chip and a package substrate. So those are another level of interaction of stress. And each of them are gonna create some chain reaction of combined stress. So that is from thermomechanical or electrochemical and thermoelectromechanical stress, and more is coming from what kind of user condition is applied for that device. Like, is it gonna be in Dubai desert? Is it gonna be in Alaska or in California? Lovely weather, right? So those one create different and kind of a stress level. So the CT mismatch between chip and the package substrate, combination of different chip size and the package size, and the influence of material property, like the CT or the glass temperature or modulus. Those are the individual factors, and the range of temperature and humidity at real application area. Like, as I mentioned, data center environment is very good, but some of devices are gonna be on the cell phone tower in Dubai desert or Alaska. So gonna get way different temperature and stress. So back to kind of history of IC packaging. I don't want to go beyond 1970s, but 1970 might be pretty good to understand. At that time, it is, I'm not sure whether it is correct or not, this era of analog. So during that time, this kind of PDIP, plastic dual inline package was one of innovative semiconductor packaging, which require a lot of engineering as well. They put the silicon chip on the metal lid frame. It's alloy lid frame made of either copper or alloy 42 type of the metal, and then some adhesive for the chip attach and connect by wire bonding. And then it goes to the through hole. So this lid put into the PCB through hole, and they got the welding, solder welding for the joint connection. So the PDIP go to through hole. And then later on, now 1980s, so our era of digital is showing up. So the dual inline is not enough to accommodate all the requirement into limited space. So came up with why we are not using all the four side. It's quad flat package. So plastic lead chip carrier, one of them is a PLCC. It's J-foam, and it goes to surface mounting. Instead of through hole, you're putting on the PCB substrate as surface mounting, and utilize all four sides of a chip and the four sides of package. So from 1980s, we got another kind of big wave. It's a PC wave, personal computer or desktop showing up. And then we need a more higher density packages which can support this technology. So came up with QFP, same quad package, but it changed the lid form to J to the gull wing. So it can offer more finer pitches space on the surface mount. And then other inside technology is similar, and they also could insert heat spreader. So this package can dissipate the heat out of the packages. the beginning of 1990s, we got the big wave, which is dot-com wave. It was very hot in Silicon Valley. This might be one of the reasons I got brought up to, I was imported from Korea to the Silicon Valley in middle of 1990s. So it is a BGA. So quad flat packages can offer only outside of the package. And the BGA can provide entire area of package for interconnection. So it could have more higher density, the functionality on the mechanism, right? So instead of using lead, it has the soldable on the package, the bottom side. So that could result in a lot of different kind of type of size of packages on the BGA. Beginning of 2000 until now, we are in the almost 2020 as era of mobile and the smartphone and Internet of Things. They say Internet of Everything. The big data cloud, AI, the VR, AR, it's coming and more. I can imagine what's going to happen next year or a year after. And this kind of demand on technologies, innovation, drive very rapid shift from conventional the packaging like a multi-chip or stacking to POP and the fan-out wearable and a lot of heterogeneous. I'll address this heterogeneous several slides later. So pace of change become very, very aggressive, more than Moore's law. Moore's is one of the old scientists running Intel. He predicts technologies, silicon node is going to change about 10 years. But now it is 5 years and 3 years, 2 years, very busy. So for this rapid in the new change in 2000, so this flip chip BGA is becoming one of core packaging technologies. So it offers the bumping, solder bump, connect die to chip, the chip to packages. And the solder bump is not enough to accommodate all the electrical or thermal or mechanical requirement. And why not copper? And we put just a little bit of a solder cap on top of copper. So this is very the general, the cross-section of flip chip BGA and chip bump connected to substrate. And it has also soldable on the bottom of the package, goes to PCB and have heat spreader to help release the thermal generated from this chip. And it's changing. Do we need this heat spreader? Then why we take it out? So lidless flip chip BGA, and it's still not strong enough to support the package, the flexibility or the rigidity. And we put molding compound. And later on, why we do underfill? Just mold compound and mold underfill at once. And it could go to very fine pitch copper filler, flip chip CSP, and then very small the wafer level packaging. So from all this, the technology we have, and all the market, and then requirement from industry. So what is our roadmap in future? How we can meet that? So in that roadmap for packaging area or semiconductor, I put two drivers, main drivers there. One is the market. So in the market, I mentioned we have infrastructure or internet, big data, cloud computing, server network storage, communication, and networking with wire or wireless. And other segment is digital consumer, entertainment, AR, VR, and broadcasting, those things. And mobile area is big market. Apple, the Samsung phone, and those one of good example, the personal communication, Internet of everything, wearable things, those also require connectivity and network. And industry still keep moving. Instrumentation, my son is working for one of biotech companies. He's telling me sometimes very kind of funny idea. How do they make some surgical instrumentation without opening the body? So a lot of technology there. I am learning from him. And the security is another important. How we can prevent hacking from, I'm from South Korea, but North Korea. And automotive and the military and aerospace. In those areas is a big driver in the market that require a lot of packaging technologies. And moving forward, is a powerful surging is AI and autonomous driving. The big data center. There might be a lot of other things, but I just put what we can realize today. And another driver is technology side. I mentioned this so briefly, performance side, density, and cost and yield is very important, especially this day, the manufacturing and manufacturability for high volume, high mix is one of important things. So the line should be able to accommodate quick change and quick setup so they can meet time to market, time to money. And then collaboration among supply chain is important. I'm the customer, but that is the previous the things. And this day, from top to bottom and the consumer, everybody work together, kind of a collaboration. So from that roadmap, let me go quickly review what kind of silicon, CMOS process technology has been changing. From 2013 until next year, the roadmap or things that happened is about around the 6 silicon node change from 28 nano to 7 nano. And then TSMC is thinking about even 5 nano of the technologies. So those drivers are cost per IO, per bit performance, and the functionality require all these new advances. But it requires a lot of investment. So if they want to change from 10 nano to 7 nano or 5 nano, it has about $300 million for one module of this process. So not many of them can do it. Just TSMC and Samsung right now can support that kind of huge investment, including their R&D resource, development effort. Reason is logic device is required for high performance microprocess and lower power. The functionalities goes up, and then silicon chip is generating more power. So for example, current Oracle, the Spark CPU, the dynamic power is a 480 watt. Even I can put my finger on that, it's gonna burn. And then most of network, the switch anticipate more than 300 watt power from the chip. So this new node help to reduce that kind of the power consumption. And According to TSMC, this year or last year, April, they anticipate this kind of improvement for density compared to 10 nano to 5 nano is more than 2x. And the power is going to reduce almost 50%, 0.6. And speed is going to improve 70%. So all these new technologies in CMOS are supporting that requirement and even beyond. On the other side, the packaging, there's a two area. One is a small form factor, and the other one is high density, heterogeneous. So small form factor packages has been innovated from this big thickness, a thick thickness, and the big body size, go down smaller, 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 smaller. Now it's very tiny, 0.4 millimeter thin, the packages. Large body size for high end is becoming more larger and thicker and high performance, but it should be very rigid to support that big body size without changing any kind of mechanical deformation. So area is a 3D IC, like stacking the die all together, 2, 3, 4, 5 dies stacked together, support high bandwidth memory. And this is 2.5D using silicon interposer. So in here, I have a simple scheme. So it's a chip and substrate. In between, we put silicon passive interposer, which can offer more finer pitches, the inner connection. This is what Intel invented, embedded bridges. So instead of having this silicon interposer, they put bridge inside of substrate in here. So it connects between two neighboring chips. Very, very good technologies. So I'm sure it's going to be hit real the field shortly. They have some kind of engineering sample and some small volume product today. And moving forward, TSMC bought one of good technology which has been developed by Invensys. So that is a wafer-on-wafer direct bonding. So instead of having this bump, this bump to bump has some space, requires some space. Like typically about 150 micron to small one becomes about 30 micron or 40 micron. This wafer-on-wafer doesn't require that larger space. Just a 5 micron pitch, 2 micron bump connection area is enough to connect 2 chips or 3 chips. And one of new ideas came by the University of Illinois and the UCLA joint study, and they have this kind of silicon fabric, silicon integrated fabric. So this day we have one memory, one logic, and some other voltage regulator putting around the big PCB. Everything put into one wafer area, like 6-inch wafer or 8-inch wafer put together, and they give it to connect to PCB directly. It's just the beginning of this idea, but I see good potential for these technologies. So I'm planning to engage with them for further study. Then what is our roadmap? So I borrowed my slide. I presented this roadmap 5 years ago in Apex in 2013. And I was scratching my head, which one might be good for San Jose State, and I retake it. So this packaging role is bridging the gap between silicon and the PCB. So PCB, the moving is not that aggressive, and it has very limited. So PCB has almost 1 millimeter pitches requirement for today, but silicon side is beyond 10 nano right now. It's a huge gap. So packaging is gonna bridge this gap between two. So those technologies are feed through all the way to BGA, and now some of the package on package, like if we break down the iPhone or Galaxy cell phone, you may see all these kind of the packaging technologies are there. So in this year, 25 to 2015 and moving forward, even within the package and substrate, the silicon and package, we need more finer pitches. So typical flip chip solder has a limitation on 150 micron pitch. But we need more and more. So it goes to 40 micron. Eventually, 30 micron is coming soon. So silicon interposer can make it happen this day. And moving forward, in 2 years later, 3 years later, everything in major area is going to be heterogeneous. So single chip, single package is not going to help to support entire the technologies need. So small body still also heterogeneous, like a multi-chip into one package. And large body also heterogeneous, the multi-chip in one body. So wafer on wafer, chip on wafer, or wafer level integration is going to happen in 2020 and moving forward. So the future roadmap until 2030, I put like this. So in 1990s, we had very kind of good technology like single chip horizon tool, MCM, not vertical stacking, without through silicon via. And 2000 until now, we have some vertical the inner connection and the multi-chip using silicon interposer. And in the meantime, Intel came up with no silicon interposer, but better the connection density. And late 2010, right now is 2018, this kind of copper-copper direct bonding technologies. So TSMC offering this, and the original, the inventor of this technology was Ziptronics. So Ziptronics sell this technology, and they came up with another better idea. And they came to EPS. I went there on last week, and the Binghamton University. It was this electronics packaging symposium. They showed another slide for advanced the copper-copper direct bonding. So it's keep moving. It offering sub 10 micron or sub 5 micron inner connection density. It's 10x higher than a standard 2.5D packages. So moving forward, I guess this silicon interconnect fabric is going to be another kind of a commerce for supporting all these requirements into one stop. And then after that, I don't know, you guys come up with a better idea and they found the garage company. So far was very good kind of a dreaming. Wow, this good technology, but there are a lot of challenges. Even I don't understand, I cannot describe what else will be happening. But in the packaging area, I put 3 areas. Thermal stress, because the power requirement is getting higher and higher. And the signal and the power integrity is also one of a challenging area. And the mechanical stress connecting different heterogeneous material into one system, small the box, is going to create a lot of different the mechanical stress. I'm not going to go line by line, but I just want to show. And then later on, I can share this slide with the college. So several years back, I thought, oh, I know these issues, and it's not a problem. But with the new technology, new silicon node, and new material, wow, non-issues become very catastrophic kind of failures. So performance require geometries changing, shifting, density is gonna be dramatically, exponentially reduced, and the packaging option is growing, and not a single chip monolithic, but it goes to hybrid heterogeneous approaches. A lot of challenges. Cost. Every company is driving cost. How much cost we can save? And what is the pros and cons? How much spend you want to spend, and how much we will gain? It's very kind of the aggressive on here, and the short learning cycle. Like we look at the silicon node development change, learning cycle now is 6 months, 1 year. We should be able to hit market directly. And so the engineer working in here, Silicon Valley, in other high-tech industry, doesn't have time 24/7. So one day when my daughter was in high school, she's in the East Coast now, she drew some picture. It's dad's life. So swimming, work, candle, work, and very small portion is sleep. So that is the life, because most of manufacturing sites are located in Asia. So after working here, in the evening or the nighttime, we on the phone to talk to manufacturing the engineers. And early in the morning, we talk to East Coast. Yeah, 3 hours ahead of the California. So what time I should wake up, what time I sleep, whenever you find the time, you take a kind of a super nap, power nap. But it's really fun. So always I talk to my colleague and my engineer, hey, we are enjoying very good working fun. Very challenging, but very good return when we release the product without issues. Wow, yeah. Go to happy hour. So let's review the chip package CPI key element. So what is the interconnection technologies? So like the old day, we have wire bonding, connect chip to package. And it goes, this pitches is still very good. Like today, they support even almost 30 micron pitches between the two. But it requires longer wire length. So create more kind of electrical delay or noise, like coupling between pin to pin. So designing this layout of this I/O signal, power ground, those are very kind of critical. Those are all electrical engineering based student may learn about. How to do signal integrity, what is the noise, how do we improve that or make it more effective. And this bump is offering like 130 micron pitches, but it got reduced the travel length, long wire length to very short. So it goes to typically about 100 micron long, and it just 60 micron between chip and package. So help a lot of electrical performance and mechanical durability by having this. And this is not enough. So change it to copper, and it can support even 20 micron with a tiny pillar, copper pillar. And the process to make it happen is this kind of wire bonding technologies and the flip chip attach by reflow or thermal compression and other new technologies. So it's a typical example for your eye refreshing. So this is solder bump, actual the image that I took. This is actual cross section. This change it to copper bump from solder to copper. It cannot be round shape. It is kind of octagonal, but we just say it around the shape. This is cross section, and after reflow, it pretty much looks same. But in bottom over here it's a copper staying there. And micro bump. Oh, this is ovular shape. From round shape to ovular shape could support more mechanical rigidity. So benefit of this copper compared to solder is more fatigue life, mechanically more durable, and electrical thermal of copper is much better than the solder. And the fine pitch scaling and also support small form factor. The manufacturing yield is better. And it also meets the RoHS 6. This is environmental requirement entire world, not to use any lead. So old bumping, solder bump has tin lead, the alloy. And then since the RoHS 6 agreed not to use lead, so we changed the metallurgy from tin lead to tin silver. And it increased the melting temperature about 20 degrees C, but this make the world beautiful. Couple example for other process technology is this kind of laser, the assist bonding. So copper bump requires some compression bonding, like a mechanical pressure required. But that requirement has limited die size or count of bump, like about 4,000 bump or 5,000 bump. But eventually, what I have today is 20,000, almost 21,000 bump within one chip. So I cannot compress for the thermal compression. But this laser is supporting, they eliminate that kind of a mechanical pressure. Just a couple seconds of the IR laser emission make it happen. And then for underfill, is very innovative the material like the TC-ACF, the anisotropic conductive film. So it's very good film without doing underfill. It can support the wafer level chip to wafer attach or chip to chip attach without doing underfill later on. And there's a lot of other technologies that is coming, and we are utilizing what the invented every day. And this is one of example for previous, before copper direct bonding, as copper tin and copper bonding can offer around 10 microns of the scale. And this is another one that TSMC now market their wafer-on-wafer technologies. But it was invented by Ziptronics and then was moved to license to TSMC. And Ziptronics changed their company name to Xperi, very nearby from here. So they are offering another advanced technologies. So every day, every morning, wow, something happened, very new, excited, in realities. So I will go very quickly in here. For wire bonding and the flip chip, next slide, and then the other slide, 2.5D, always have a similar type of challenges. The silicon damages during dicing, and during the wafer proving, some pad damages, and moving forward, it's going to create die attach or substrate delamination during actual the application. Die top delamination between this molding compound, encapsulant, and die surface, because it is different material. So eventually the shrinking and then the relaxing is going to be different. So the interface going to be subjected to very high stress, and boom, critical failures. And stress go into the silicon inside, and create inside ultra low K delamination, and then this typical the second stage the issues, substrate delamination. So whole this area is one of the responsibility for packaging technology engineer to look at, to prevent before, ahead of time. When it happens, it's too late. We got to hold the line, shut down, and then fix problem and then release it, and we lose money. Flip chip has also same kind of failure. And instead of wire bonding, it using bumping. It has another problem. The bump crack or the delamination and the bridge between the bump and bump. Also, the bump is connected to I/O pad directly, so it has more higher stress than wire bonding, and this kind of a low K area of delamination, so-called white bump, has to be considered at the beginning of the design. So this is like a white. And SOP, solder on pad crack, and UBM side crack. It's happening. So high power devices like CPU and the server chips, network, over 300, close to 500, need a big heatsink. And then the pressure, loading pressure is about 500 pounds. And this package should be able to survive from 500 pound pressure, not one day, 10 years, 15 years. So the designing of this package and this PCB board and the entire system is also one of area that we are studying. With some crazy photos, images, but this one is done by some modeling. So at the beginning of design of any device, any package or system level, we do some modeling, find out what design rule is better, not to have a hot spot or higher voltage, and what the layout could have more less noise interconnection in terms of signal integrity. Which bump type and which the bump density could have a less tensile stress or mechanical stress in between chip and package. Those are all done by modeling. So student may think about this modeling as one of the good area to study. And adding this modeling capability, and then the process is going to be multifunctional, the guys. So mechanical modeling and the material modeling and the process technology, the multifunctional engineer is always and any place is welcomed. So it is 2.5D using silicon interposer. They have a two process, chip first. Chip first is putting this logic chip and memory chip and other functional chip onto silicon interposer. So chip first. And one by one, and here, each block. And it goes to mount on wafer, and then have this bumping, and eventually gonna have putting on the package substrate. It's chip first. So it's one of the beautiful thing, the images, but it is real product now, even 2015. It's in production and volume production. So chip last is putting on the good chip, known good die onto the interposer may create unexpected yield loss, which is another cost because we're gonna scrap this all good dies, good chips. So instead of that, let's put interposer onto the substrate first. Then test this interposer substrate functionality, and then putting known good die one by one. So that is idea for chip last process. So challenges there, but I put yield in top. So people saying, what is the cost? What is the cost? But hidden cost, the big cost is yield. So cost is king, but I say yield is God, whether you like it or not. And then the known good die strategy is another area that we design the process from the beginning with. And having that 2.5D package, always the interposer goes to very thin, like 50 micron or 100 micron thin. So it is not A4, the paper. It is real wafers, thin the wafer with 12 inches, 300 millimeter. Like on this, weaker than the real paper. And the work page change is very important, anytime, any place. And this work page control should be within some range, through the entire temperature range, from room temperature, go cold temperature, and high temperature over 200 degrees C. We need to have it less than below 10 micron work page. Otherwise, it's gonna create failure in the integration of the package. Reliability, we have much better material replacing solder, but still has a lot of challenges, like electromigration. So this current density is over 100 milliamp or 150 milliamp, with the temperature is a kind of operation junction temperature is about 100, 110 degrees C. Then the material solder between copper is gonna migrate and have this kind of failure. So this material science is important to get this kind of the metallurgy, the make beautiful. And having all those 2.5D packaging, there are a lot of another areas and challenges we need to look at, like the wafer thinning, handling those 100 micron thin wafer, and the micro bumping technologies, what is the joint informality. So one wafer, even one chip has over 20,000 micro bumps. So the bump height should be controlled within 5 micron. Otherwise, some bump is gonna be open and some bump gonna be very compressed. So open or cold joint. And the backside of TSV wafer process. It's another process challenges. 3D stacking challenges. One area is particles. I work with a lot of the manufacturing sites like TSMC, wafer fab, and other assembly. And always particle is the troublemaker. So when they have a Pareto breakdown of the top 5 defects, I recommend them, no, you control particle, then your order of the Pareto is going to shift. So this is always a troublemaker. And the second one is warpage, and then other handling kind of process is challenges. I guess I exceeded time about 5 minutes. Sorry about that. So this is my last slide. So what is our role in working on the packaging technologies? We gotta support entire the Internet of Things, connected everything, cell phone, car, home, and the cloud, and autonomous driving. And eventually, this cloud gonna have a private cloud and the public cloud, keep all the information in security. And first thing is, we're gonna enabling everything possible, from small form factor, like chip scale, to high-end, high-density packages. So it's one of given missions needed to achieve, accomplish. And integration methodology and metrology. From the beginning of it, we gotta think about how do we attack the problem. What is the best way for metrology? So design for manufacturing, design for reliability, built-in design rule, and come up with roadmap. And the convergence and the bridging gaps. So gap is still there between package and the PCB. So we gotta work together, hold this manufacturing, not by myself. Let's work together from wafer fab and interposer and the package and PCB, and then it's my user who is doing real, making the system board available, surface mount, and co-designing. So previously, IC design engineer just tape out, finish his design or her design. This is I/O, this is a signal and the power ground. And the packaging engineer scratching head. Oh my God, how do I lay out my bump? And how do I lay out my BGA for the PCB? But now it cannot be. So everybody has to work together. So this is my design, any idea, and then accommodate other requirements and adjust and make one agreed upon designing. Solution development from supply chain all the way to industry from the beginning. So I'm packaging, but I have to talk to my customer and then find out what is their requirement and who is their the consumer. And so in summary, that is collaborative cooperation, all the engineering area and concept to product, but important thing is from next 5 year, 10 year, academia and industry collaboration is really needed. And we're gonna make all this happen in beautiful, very convenient. This is my talk, and sorry for taking, but I'm not sure what is the percentage of your understanding. Any question, please?
All right, thank you, MJ. So I think in the interest of time, we'll keep MJ here if folks want to come down and ask questions. If you have some questions, rather than do the open Q&A, because we're already past 1. For those who want to try to get some go points, please feel free to take a selfie with this as your backdrop. Not necessarily MJ, he'll be busy answering some questions maybe. But thank you everybody for coming, and hope to see you with the next one.